Alternators, paralleling multiple units. In this presentation, we're going to be looking at how we synchronize more than one alternator together. So we're going to look at synchronizing, what it means, synchronizing gauges, synchronized alternator characteristics, and why do electrical grids crash or black out. When an electrical load exceeds capacity of a single alternator, parallel operated alternators are required. When AC sources are connected in parallel, they must be synchronized. And we run into this in many different situations because often all of the electrical AC generation is not from one single source. Instead, it's multiple sources that are all connected together in parallel and which must be then synchronized. Synchronizing refers to the paralleling of multiple AC energizing sources, and they must have the same phase sequence, as in A, B, then C. They must have the same frequency, example would be 60 hertz. They need to have the same terminal voltage, which could be 208 line value, and they need to have phase voltages that are in phase. Now, the last one could be a little bit tricky to understand, so we're going to look at a visualization of each of these four different characteristics. First, phase sequence. What I have is an operating alternator and an incoming alternator. Phase sequence indicates that I need to have phase A connected on the operating alternator to phase A of the incoming alternator. And if we look at the top here, we can see definitely if I were to hook that up to the disconnect, that would be wrong. So instead, I need to change the phase sequence so that it matches the ABC of the operating alternator. And there we are. Now, this switch that I just referred to as a disconnect is actually going to be the synchronizing switch. When it closes, it will electrically connect the two sources together and they will operate in synchronism. So there we go, I've connected it up and the phase sequence is now good. Now remember, there are three other characteristics that must be ensured prior to throwing or closing that switch. So next one is frequency. Now the operating alternator is at 40 volt, 60 hertz. The incoming is at 208 volt, 50 hertz. Obviously the hertz needs to be increased. And the way that we increase the hertz is we increase the speed of the prime mover on the incoming alternator. I speed it up and then I am operating at exactly the same speed as the operating alternator, and that would be 60 hertz. So now the frequency is A-OK. Next item, voltage. Obviously, my operating alternator is operating at 480 volts, whereas my incoming is only at 208. I need to increase the voltage on the incoming alternator, which means I need to increase the DC excitation so that I have a voltage value that is equivalent to the operating alternator. Now they're both operating at 40 volts, line value 60 hertz. Finally, I need to now address voltages in phase. And what I mean by that is that if we look right over here at the top, right where it says 40 volts, 60 hertz, when the red crosses this line right where my little mouse is waving up and down, I want to have the other incoming alternator also have a cross at exactly the same time. And so we can see very obviously that they don't. They are slightly out from one another. And so what we need to do is bring them in phase with one another. And what that means is that we need to adjust momentarily the speed of this alternator so that they are exactly in phase. It's sort of like two cars driving down a highway. They can both be going 100 kilometers an hour, but one could be ahead of the other. And so in order to get both the cars at exactly the same place on the highway where their hoods are lined up and you could wave to each other through the window, one would have to slow down slightly for a short period of time, or the other would have to speed up momentarily for a short period of time. So we're going to adjust the incoming alternator speed slightly for a short period of time to get the phases identical so that they're in phase with the operating alternator. So now we can see A and B and C are crossing the same point or occurring at exactly the same point as for each alternator. Great, so now we've got all of these different items exactly the same. And what we can do now is we can synchronize the alternators. Synchronizing means that we are now closing this switch and the two alternators will now operate in synchronism, as in they operate exactly the same together as if they were one large alternator. So just to remind us, to parallel multiple alternators, they must have the same phase sequence, the same frequency, the same terminal voltage, and they must have phase voltages that are in phase with one another. Now, to assist with this, because, well, the animation works fairly well to show us the differences, but in the real world, we can't actually see all of those different items shown in a different physical form. Instead, we need to rely on different gauges. Gauges that are used to assist in determining when to synchronize are voltmeters, frequency or hertz meters, synchroscopes, and something called a 3-lamp assembly. This could be a common synchronizing gauge assembly, where we have a frequency meter, a synchroscope, and an AC voltmeter. Then at the bottom, we have a switch, and the switch would allow us to close and to bring the second alternator online in synchronism with the first operating one. Now, voltmeters are pretty straightforward. We all know how a voltmeter operates, and we could have a voltmeter for both the operating alternator as well as the incoming alternator. And we could adjust the DC excitation until both AC voltmeters registered exactly the same value. We could also adjust the frequency on the incoming alternator so that it was exactly the same as the frequency of the operating alternator. The synchroscope tells us the phase, if our voltages are in phase with one another, and how much I need to adjust the prime mover speed. The dial on a synchroscope indicates if the incoming alternator is either too fast or too slow, and so in a way it helps to establish the frequency. When the dial points at 12, so vertical, the unit is ready to synchronize. So it'll operate like this. Could be really the incoming alternator is way too fast, or it could be like this, the incoming alternator is way too slow. And as I adjust the prime mover speed, the speed of the needle will then adjust also. If I get it dialed in really good, I can then pause it or get it so that the needle doesn't move at all. And at that point, it's indicating that the difference between the two alternators is almost nothing. And so a synchroscope connects to not only the incoming alternator, but to the running or operational alternator. Now, the second item that I need to be aware of is something called a 3-lamp synchronizing switch. Now, a 3-lamp synchronizing switch is essentially a switch with a voltmeter run across it, or more likely, a light bulb. Now, synchronous switches should only be closed when there is 0 volts across them. And that would mean that there's no potential difference between the incoming alternator and the operating alternator. And so although we could put a voltmeter across this and close the switch only when there's 0 volts shown, it could be much easier if I simply connected a light bulb across them. The light bulb will then go dim or not lit when there's 0 volts across them. And that can be an easy visual indicator to us that now, since there's no voltage difference between the incoming and operational system, that I can close the switch. In a 3-phase system, I simply have 3 independent lights, 1 light for each phase. Now, there are 2 different 3-lamp methods of connection. One of them, called the 3-dark lamp method, is a little bit more common than the one below, 1 dark, 2 bright lamp method. So let's first take a look at the uncommon one, and then we'll focus more on the 3-dark lamp method. In the 1 dark, 2 bright lamp method, when the top lamp is dark and the remaining 2 lamps are bright, the alternator can be synchronized. And you'll notice that there is a difference in connection from here going between C and B, and here from B down to C, and this one is just across A. And so this does have a few advantages over the second one that we're going to look at, but it is far less common and usually causes a little more confusion than it does clarity. But to recapture, what it is intended to provide is a visual indicator. And the indicator tells the operator to close the switch when two of the lamps are very bright and one is very dark. The one that's more common is called the 3-lamp indicator method and 3-dark lamp method. This is the one that we looked at very beginning of the discussion, and we have a light mounted across each one of the switches. Now, this won't tell us if there is a difference of phase, in phase or out of phase, but what it will show us is a few interesting aspects. So first, it will tell me if the incoming alternator is the same frequency, and it will tell me if I have the wrong phase sequence. So perhaps I've accidentally hooked up A and B wrong. If I have the same hertz, but I have this where it's going through sort of a Christmas tree effect, that would mean that I have the wrong phase sequence. And that would mean that perhaps B was up here, A was here, and C was on the bottom. If they're going in Christmas tree, it isn't working right. If they're not in phase at all, they're all going to be very bright. And that also would not be a good situation, and I would not want to close the switch. They could all be dim even, and again, that would indicate that they are not in phase. If I have very different frequency, but my phase sequences are correct, I would get something that looks like this. A very quick sort of flashing almost, where the lights are coming on and off, but they're coming on and off simultaneously. If I only have a slightly different hertz, then what we would get is something like this. And this is really what I'm trying to shoot for as the operator. And what I want to do as the operator is I want to close the switch when all 3 lights are de-energized or not illuminated at all. And the slower I can get them to flash, the easier it will make my job. So when all lamps are dark, the voltages are in phase and the alternator could be safely synchronized. So to conclude, we have an online alternator, which sets the voltage, frequency, and everything else about the system. When I bring on an additional alternator, I could choose to use the 3-dark lamp method or the 1-dark, 2-bright lamp method. In modern systems, you may run across something like this, where we have a frequency hertz between the bus and the oncoming alternator. In this photo, it is abbreviated as the generator. And then we have voltage. There's the bus voltage and the generator voltage. We have basic buttons to raise and lower the voltage, basic buttons to raise and lower the speed, which would affect the hertz. And then here we can see a digital synchroscope that gives the operator an indication as to the speed of the incoming alternator. Then down below his hand, we can't really see it, but there would be another push button that says push to close. And push to close would be the circuit breaker. Right now, it's open. When it's closed, the green light would go off. Now, there are many different situations where this would be desirable. When we have multiple backup generators at a facility, if they're operating in parallel with one another, they will have to be synchronized. And often this will be done automatically without the use of a person with push buttons and looking at dials. It could also be in a larger facility like this. This is more an automated system where we have multiple generators that are going to be connected together in parallel and synchronized without the use of individuals. Now, synchronizing alternators is a time-consuming procedure, which is not really done unless it's absolutely necessary. If the main grid requires more power than what a single alternator or generation station can supply, more alternators must be synchronized, so you won't have much of a choice. But instead of synchronizing the alternators as the power demand increases, which could be seen as time-consuming and expensive. Alternators can be synchronized one time to the grid, then left connected and quote unquote float. And that means they're not supplying power, but they're still synchronized. Let's take a look at what that actually entails. And in order to discuss that, we need to really have a discussion about how the system will function once they're synchronized. So individually, a single alternator is not able to change the grid voltage. And individually, a single alternator is not able to change the grid frequency. Individually, increasing the prime mover torque of an alternator will result in more load being taken by the alternator from the grid. And if we consider what the prime mover could be, it could be gas-fired generation, or it could be hydro, so water flowing through a penstock and turning a turbine. Really, what we're talking about is on a prime mover, increasing the watts of energy to create more torque. And the torque turns the alternator, which then takes more of the electrical load or generates more watts. Now remember the additional floating alternators we were referring to before. When synchronized, the rotors of the floating alternators are not spun by power from their prime movers. Instead, power from the three-phase system is magnetically turning the rotor and the prime mover together. If the grid three-phase power is used to turn the rotating assembly of the floating alternators, they are actually acting as a load to the system. So bear with me, it's a little bit confusing. So here is a loaded alternator, and it is supplying all of the load for the grid. Now, we also have floating alternators that are synchronized and coupled to the grid. Notice the arrows that I've shown here. Right now, this one is providing all the power. It's providing power to the load, but it also has to provide a little bit of power to each of the floating alternators. And that's because these alternators are synchronized, but what keeps them synchronized is the electromagnetic flux around the stator that locks the rotor in place and keeps it spinning at exactly the same rate as the loaded alternator. To divide the load between two alternators, they must work in unison. So let's say I want to split the load, which is here, between alternator 1 and alternator 2. Well, alternator 1 would need the prime mover torque reduced, so essentially easing your foot off the gas pedal of alternator number 1. But simultaneously, alternator 2 would need to have the prime mover torque increase, so pushing down on the gas pedal of the second alternator. And so a substantial amount of coordination and communication is required in order to achieve this seamlessly. So I'm going to load my second alternator by stepping on the gas, and I'm going to now share the load between the two alternators. And we remember did this by coordinating and easing off of the prime mover here, while increasing the prime mover's work on this one. Now alternator 1 and 2 are equally loaded. To divide the load between all four alternators, they must again work in unison. Alternator 1 and 2 prime mover torque must be reduced, while alternator 3 and 4 prime mover torque must be increased at the same rate. And so we can see how this would be, again, a coordination series of events that would need to take place, and then we could load all of the alternators equally to supply the load on the grid. But leads us to a question that often comes up. Why do electrical grids crash? Well, let's take a look at another example with exactly the same system. In this system, we have four alternators. All four alternators are loaded to, let's say, approximately 80% of their capacity, and they are supplying a ginormous load. If we consider how all of these alternators are connected back to the grid, they're not all within, a couple of feet of the grid, but instead between alternator 1 and 2, there might be hundreds of kilometers of transmission lines. and between 2 and 3, another couple hundred kilometers. But there would be transmission lines all over the place connecting these alternators back to the grid. Back in 1998, an ice storm went through eastern Canada and the southern states, and it took out different portions of high voltage transmission lines. The result of that is that it disrupted the generation capability and then left an alternator islanded, as in not able to supply any energy to the greater grid. Now, take a look at what happens. Now, all of the load is now being provided for by 3 alternators. And remember, these alternators were only operating at 80% of their capacity. So now they are supplying more than what they're rated for, and they will become overloaded. Now, if it becomes overloaded to such a point that it's beyond its operational characteristics, the overcurrent will protect the alternator by opening. And the overcurrent is the same as any other overcurrent. If too much current flows, the OC will open. Now, if this alternator here fails and drops offline and the overcurrent opens, well, now we've just compounded the issue, haven't we? Now these two are crazy overloaded. There's no way they're going to be able to continue providing all of the power that is still on the grid. And what we get is a cascading series of events where more and more alternators start to get taken offline because they cannot produce enough energy or watts to sustain the load on the grid. So remaining alternators cannot maintain the load, overcurrent protection disconnects them from the grid, and now our grid has gone down to 0. So in order to restart the whole sequence, guess what? We've got to repair the down transmission lines. We've got to start one alternator to energize the grid, and then slowly we need to add alternators by synchronizing them. And then as load is added to the grid, we need to start equalizing the load across all of our alternators after they're synchronized. Quite a time-consuming task, and one that we really don't want to ever have to encounter.